Okay, welcome to Environmental Systems Engineering 408. Unfortunately, I can't be with you today. I'm in Albuquerque, New Mexico, at a review meeting for a carbon sequestration program. But I will be here on Thursday when we can get together and I can maybe answer in person any questions that you might have. So the class is on contaminant hydrology, as you can see here. And what I want to do today is really talk just about the delivery of the course, what the actual deliverables are from the course, its scope in terms of the topical matter, and in the mechanics of how we will prosecute the course. This is a class that's now been given since 1996-ish, so of the order of 20 years. It's a blended class in that it's presented both in person in classes and also online. It's possible for you to take it in a completely online mode, as we'll discuss a little later. The class meeting times are 1:35 to 2:50 on Tuesdays, Thursdays. We'll meet in Sackett, and our first meeting, I guess, will be on Thursday at 1:35. But almost all of the materials are delivered to you either through the course website, which is this second one here, or through Canvas, where a number of the quizzes will be completed. Many of you, almost all of you, I don't know if all of you, many of you will have taken EME 303. The delivery is similar to that. I would say that the rigor of the exams for a big class is slightly less, in that it's a tools class for you to learn something about the craft that you might end up applying once you graduate. It is a elective class. It's not required in your program for the environmental systems engineers, and it's certainly elective for other programs. And so depending on whether you like the methods of presentation and the course material, you should make a decision as to whether you might want to take the class or not. So don't dissuade you from it, but it's just to stress the fact that indeed it is an elective class. The topical area is one of contaminant hydrology, and so we have a single text. We've used this for a number of years. It's the text by Feder. It's available in the bookstore. I don't know exactly what the price is. We don't teach from that text, but many of the figures that are used in our notes actually originate from there, and so it's a useful backup, I think, to understand some of the material. And there are also some texts in the EMS library. These are the ones that are noted on the back side of the syllabus. None of which are necessary, but all of which are available just to provide extra details should you be stumped by some particular problems and would like to understand a bit more about the topical area, which if you are working in the groundwater hydrology or contaminant remediation area, are certainly texts that you'd find useful in applying your career. I didn't introduce myself, but if you don't know who I am, because you can't see me on this recording, my name is Derek Ellsworth. My office is in 231 Hosler. The TA for this class is Cheo Yuang. Our offices, as you can see, are right next door to each other. You should probably go to him first. He might give you a better reading than I. I have an open door policy, and so my door is usually open most afternoons, and so if you catch me there and you need to see me, then you're welcome to do that, and I'll be happy to chat with you. But I would encourage you to see Chayoe if you want to resolve some of the kind of standard questions you might have for homeworks, etc. The class is a follow-on to groundwater hydrology, so a prerequisite for this is 452. I don't enforce prerequisites, so it's up to you. You can certainly review all the materials that we have for this course online and decide whether you are comfortable with that material. And if you want to discuss with me whether you are competent to continue, if you haven't had 452 or are taking it concurrently, then I'm happy to do that. But it really, since all the material's online, you'll be able to tell, I think, whether you have the tools to be able to succeed in this class. The scoring for the class is split between a number of basically weekly assignments, which are offered, which come live on Thursday every week. You have a week to do them, and they're due the following Thursday. Typically, you have the material to be able to do them after the first week. So the first one will come live this coming Thursday, and it'll be due a week Thursday. There's a midterm exam that is set for the Tuesday immediately before spring break. So this is spring break it'll be the 30th of February. Spring break is the 5th to the 11th this year. And so we'll have the exam on the Tuesday, and then the Thursday, if you're making plans, will be free to be able to do whatever you need to do. We'll talk a little bit about the prior exams, and all the prior exams are available to you, not solved, but are available to you to be able to review. There will be, for each of the 18 or so classes that we have, there's a content quiz. If you come to the class, you get a free buy on that. You get 100% on the quiz, and you don't have to do it. If you choose to not join us in class, which is your prerogative, then you just complete the quiz. The quiz for Tuesday will close on Thursday at midnight. The quiz for Thursday will close at Tuesday, following Tuesday at midnight, and the scores for those go into your final grade. And the one major delivery for this is this remediation presentation, which you'll be assembled into groups, 6 groups, each of whom will look at a different remediation suite of methods and summarize those for presentation within the class to your peers. And so that will be worth 25% of the grade. The grades together total 100%, and as I say, the content quizzes, if you choose to come to classes, you won't have to do those except for when the material is actually transmitted to you online. And so that's kind of the way in which the class works. As I say, it's a blended class. It certainly will be partly online for some of you, and could be completely online for those who choose to do it that way. So that's kind of the general layout of these. The grading divisions are standard grading divisions, maybe a bit more generous than the standard Penn State one, which I think has 94% as an A. Attendance, as in all Penn State classes, is encouraged but not mandatory, and certainly some of the class is projected to you remotely. The usual requirements for academic conduct of collaborating with colleagues, working in teams, working jointly, but ultimately submitting independent work, I think is something that's important to this class. And so for those of you who are, let's see, this is I don't know why I did that, but anyway. But for those of you who are not familiar with this, all the work that you should submit should be ultimately your independent work. So that's kind of the outline of the class in terms of how we prosecute it. There's a schedule in which the portions of the class which are online and in class are defined. So these are the individual topics which follow the material which is in the course notes, which I'll show you how to access shortly. Today is online, as you know, but Thursday's class will be in person if you choose to come to it. I'll hand out a syllabus at that time, which is kind of a contract between yourself and Penn State, basically. And the periods for the online portions of the class are these central periods in the middle of the semester. The presentations for the group presentations after you've prepared them will be in April, and there'll be 6 groups, and so 6 presentations, and we'll probably ask you to be present for those, because this is part of the class material which will be presented by your colleagues and peers, and so it's an important part of the class for you to be able to absorb. And so this is the one deliverable that we talked about here. Okay? Trying to think what else we'll talk about. So that's basically the conduct of the class. Certainly you'll have seen this material or material presented in this same blended way before in your careers, and I think it's relatively standard. The topical areas are maybe 8 or so. The final one on remediation you'll do yourselves in terms of these different methods, but the other material will be presented to you. Later on in this session we'll go through an overview of where contaminant hydrology fits into society and what the important problems are that it deals with. And the course is really divided between a variety of modules. First of all, following on from Geosciences 432, groundwater hydrology, we'll continue talking about physical groundwater hydrology. I guess the difference was that instead of talking about it broadly in terms of water supply, we'll talk about multi-phase flow, where you have two fluids which may be either miscible or immiscible relative to each other. And so our main concentration on physical hydrology will be talking about multi-phase flow of oil and water, for instance, or air and water. They both behave in the same way. How they move in porous media, and more importantly, how they move in fractured porous media, where fractures are really fast pathways for fluids to move. Once we've talked about the physical hydrology of those multi-phase systems, we'll talk about the transport of contaminants, how they are dissolved in water, how once they're dissolved they're transported by both advection and diffusion, and how they ultimately may be retarded in their advance or attenuated in their advance by their interaction with the porous media that they flow through. And so this will be basically looking at the transport of contaminants and its attenuation in the subsurface. An important part of behavior is also in the transport of gases in the subsurface, especially in the vadose zone, in the shallow zone immediately below the ground surface. And we'll talk about the motion not just of water, but also of contaminants as free-phase materials, dense non-aqueous phase liquids and light non-aqueous phase liquids as they move through the vadose zone into the groundwater zone, and mechanisms by which they are held within the vadose zone and the groundwater zone, and how they are retarded as they travel within the mass movement of the water as a carrier agent. So that really physically talks about all of the physical processes by which contaminants can actually be transported in the subsurface. We'll talk briefly about mathematical models and how those can be used to solve complex boundary value problems and initial value problems to look at the evolution of groundwater plumes in the subsurface. And then after we have completed that, then we'll talk about going back to understand how you go into the groundwater aquifers and say something about the important properties which govern the transport of fluids. So the first topics 2, 3, 4, and 5 will define all of these processes in terms of some physical parameters which control this behavior. And so the question of how you recover those parameters from the subsurface remains an open question. So when we talk about aquifer and aquiclude characterization, aquifers being the units which carry the fluids, aquicludes be the units that protect groundwater resources from contaminants with low permeabilities. What are the important parameters that we have to recover, and how do we do that? We do it through direct sampling by drilling and sampling and installing instrumentation in the subsurface, and we also do it by using a variety of geophysical methods. So we'll talk separately about both direct sampling and geophysical characterization of the subsurface to be able to define exactly what the aquifers and their aquicludes look like. And then the part that you'll do will be looking at remediation divided between these 6 areas that we'll talk about a little more in a few minutes. So that's basically the layout of the class. And so most of the material is served, well, almost all the material is served to you on one of 2 sites. The first site is a home page that is really all the resources that you need, and that site also connects you to Canvas, which is the quiz engine and also the submission engine for the assignments if you choose to so use it. The layout in terms of the timing of the different components of the class are shown on here, and so certainly until mid-February we'll be meeting in class if you so wish, and not if you don't. And then from the middle of February onwards there'll be a portion which is served to you online. Okay, so that's kind of the background of the materials that that we'll talk about. The 2 sites which are the sites that will serve the materials to you, you can find just by Googling my name. And the first site that will come up, I guess that's not quite the way it works, is it? So if you put in my name and spell it right, then it will give you up a list of potential sites. It's usually the first one. And 408 is this site here. And so if we look at this, if I make it a little larger, so you can see what's going on here. Everything that we've talked about today has been on the syllabus, which is online. The syllabus links directly to this same YouTube channel, which you don't necessarily need, but I guess that wasn't the one that I really wanted. The resource page is this third one down, which is exactly this page again. So, whoops. Yeah, I guess that's fine. You can see that quite well. So the syllabus is online. In the same way, the course notes are all a relatively large file, 80 megabytes, but include all the notes that we'll use in the class that will be used. And so they're maybe not the prettiest notes, but they're actually quite functional, and you'll get to use some of these today. This, you can look at this, but it's the same material that's there. I'm not going to spend any time on that. And the YouTube site is the one that has all of the various videos on them if you so wish to review them. But I think by far the best way to access them is through this topic by topic portion. So, and you've seen, hopefully you've seen some of this before. The assignments, as we mentioned previously, the assignments, there's one assignment per week. Comes live the Thursday of each week and is due the following Thursday. And the first one will come live this coming Thursday and will be due the following Thursday. So that is as expected. All of the prior tests are online. They are unsolved, but they're present online. The class used to have a final exam and a midterm. Now we just have a single midterm. Last year's midterm is this. And you could review that to see how comfortable you are with it. The midterms are always 3 questions. The first question is a definition question where I'd ask you to say everything you know about each of these 10 terms. And the other 2 questions are calculation questions to be able to do a design for a groundwater transport, flow and transport system. The material that you need for the test is pretty much covered on this 2-page review sheet. Actually, only a portion of this you'll need because part of this, probably the part on Vado's zone behavior, we won't cover maybe until after the midterm. So a portion of it is included on that. So the deliverables are the assignments, which I think is 35%, a midterm exam, which is 25%, so these first 2, The remediation tutorial is something which is a group project where you'll make a presentation, and the rubric for this is to choose one of these remediation methods, one of these 6. Actually, you don't choose it. You'll be assigned groups and you'll be assigned a topic within that group. But to create a presentation which addresses each of these 6 components. Talk about the physical mechanism by which the remediation method works. Talk about what factors influence whether it can be successful or not. Talk about its current status in terms of how it's used and implemented in the field, in terms of current usage. Talk about demonstration projects that have shown whether it can be successful at field scale or not. Identify the kinds of conditions under which it can work, which are typically defined in terms of permeabilities, high or low of the aquifers or aquicludes, and the depths at which it's applied, whether it's shallow or deep depths, and to talk about the expense of remediating aquifers using that particular technique. So these 6 methods are germane to talking about describing it to your peers, and then the final portion is a peer review to be able to make sure that everyone in the group is contributing in a useful way to the activities of the group. And so that would culminate in a presentation in some order in April. A presentation by one group would take a whole period, so an hour and 15 minutes, and typically you'd get questions from your colleagues during that presentation, and there's a peer review also to go after at the end of it. Peer review form, I think this doesn't download, I think it downloads as a Word file, and so that'll be something which is also a deliverable. So those are the activities. During the course of the year, the 2 things that will happen will be you'll have a weekly assignment and also the ability to submit quizzes. So all of these are submitted online. The vehicle for this for us these days is Canvas, which you'll probably be familiar with. And the website for 408 is up and running. I don't know that necessarily this is the view that you would get, but what I plan to do is that each week I'll give you an update on what the deliverables are for that week. This is the one for this particular week, which you will have seen already. And in terms of the various assignments that we have, they fall into 2 main categories. The assignments which are due 1 per week, and this is just another way to access them. It's exactly the same assignment as we just looked at directly from the other resource page. And the other component would be this quiz, which would talk about the content in the particular lesson that we're looking at. If you come to class and it's not an online week, then you don't have to do this. Sign a piece of paper or make a list of the people who are present, and you'll get 100%. But if you choose not to come to class, then you have to do this. And they're typical questions that just make sure that that you're paying attention to this. And so it's completed in the same way as others. And so it'll give you something out of it. I'm not sure exactly how it comes back. It'll tell you that all of these, except for one, were unanswered, and that you actually got one right in this particular case. So take that home and use it if the question hasn't changed. So those, I think, are the main components of this as we go back to this. So everything is served to you online. I don't know in terms of if you go home to this. Yeah, they don't come up now, but certainly you'd have a calendar that would show the order in which these things are available to you. And as I say, each week there'll be a week listing of deliverables that you might want to conform to. As in other cases, the quizzes will close and they won't reopen, I think there's probably more flexibility on the deliverable of the assignments. I know that my way of dealing with assignments is that so long as the assignment is completed by the time I'm ready to grade it, and Xiaoyi will be grading it, then it's not a big deal if it's a little bit late. Most students historically have chosen not to upload the assignments onto Angel or Canvas, but to hand them in person, either in class on Thursdays or taking them directly to 203A Hosler, where Xiaoyi's office is, either that day or sliding under the door on Thursday evening, depending on how ready or not you are for it. And so that's it. So we've covered a fair bit of ground, I think, in this. But most of these things, almost all of this material, is included on the syllabus, and so I can answer questions on Thursday if you have them. Nothing of any great importance has to be done before then. But what we will do is, following this introduction, we'll have a segment that looks really at kind of the big picture of contaminant hydrology, why it's important in society, and what the key issues are in contaminant hydrology. So that will follow.
So let's talk about some projects. So I was reminded of this. In our household we have 2 parties a year. We have a summer solstice party where I roast a pig, getting up at midnight, my own firewood, cut with my own hands, stay up until 5 o'clock in the evening the next day when it's served, which is a hell of a lot of hard work. This year we got rained out, rained from 3 o'clock in the morning, non-stop deluge until 7 o'clock in the morning, put out the fire. Winter party is winter solstice, so they're both on the 22nd of June and 22nd of December. I was reminded of one of the people who come to this, Ed Miser, who owns a consulting company, hydrogeology consulting company in town. We did this project together. It was 1994. It was 21 years ago. But this was a project where New Enterprise Stone and Lime in Roaring Spring near Hollidaysburg, for those of you who are local, is a big limestone mine where they sell limestone as aggregate and make cement out of the limestone. They exist with a quarry on a structure that looks like this. It's a syncline, a fold that comes over. It has a shallow limb and it has a very steep limb. And where this material has been bent in the hinge of the fold, the so-called hinge of the fold, it's a fracture zone. And so if you can imagine it in this perspective, this is this same fold, is that within this fractured zone here, which is all busted up rock, it goes down on a lineament. And if you look at State College, the place where State College Borough gets all its water from are these fracture zones that intersect each other. You put the well at the intersection, completely busted up. It sucks water into the fracture zone from the big volume around it, and it's the most effective way of getting water out of the ground. If you put a well not into a fracture zone, you'd get 1,000th of the yield, something of that order. The originator of this idea of prospecting is Dick Parazek, who's just retired from Penn State. But New Enterprise had a quarry that was quarried out on the left-hand side of this. This was their quarry. Originally the ground went here, and now this was their quarry. They wanted to deepen it. Appleton Paper Company, Roaring Spring bottled water comes from the spring in Roaring Spring. Appleton Paper Company are a pulp paper company who use the lion's share of the water. All of their water comes from down this fracture zone into the spring. They took New Enterprise to court because they didn't want them messing up with their supply of water. It went to mediation with DEP. And basically the question was, if you have water flowing westwards in this until it hits these vertical beds here basically work as a groundwater dam. So if you imagine this as a dam which is impermeable, water flows in here, it flows into the fracture zone, and it merrily flows down the fracture zone and wets the Roaring Spring. That is the source of the spring. It's down this. they're worried by deepening this that you'd break up this dam because this would kind of displace, and as a result of this, it would no longer be a groundwater dam. No longer would all the water come down here, and they'd lose their livelihood. So we did some work with them to kind of figure out what's going on, and the kind of common sense solution was one that you could probably just imagine. We did some analysis to see what's going on, but the common sense solution that was a compromise solution was, well, why don't we go down, instead of going down 200 feet, let's go down one bench which is 30 feet, and we'll monitor what's going on, and we'll see what's going on. If there's no problem, then maybe we'll go down another 30 feet, and so on. And that's basically the solution. And gratifying from our December the 22nd party is that neither of us are in court or in jail, because it's still absolutely okay. And so that's good news. So, local groundwater. Another project actually I worked on actually about the same time, also 20 years ago. If you look at India, this is a little cameo of the Indian subcontinent. Madras is now Chennai, right? Double N. They went back from there. No. Mumbai. No, it is Chennai, yeah. Madras is Chennai. And so they went back to their previous names before the British completely screwed up their names 2 centuries ago. Yeah. So there's a very big lignite mine there. It's close to the surface. It's right next door to the Bay of Bengal, which is over here, about 30 kilometers away. And they have dug a hole to be able to dig out the coal. Coal actually sits kind of underwater because there's so much water coming in from groundwater. They can't pump it out fast enough. But because they pump so much water out of here, there two things have happened. One great thing is, as you go from it is Chennai. If you go from Chennai to Neyveli, all of a sudden you go from basically semi-arid to the most verdant, green landscape you could imagine, and it's because all of this groundwater is being used for agriculture. It's great. The bad thing is that in drawing down water by sucking it in here, is that it's pulling in water from the coast, which is pulling in salt water from the Bay of Bengal, which ultimately will impact people's wells who are closer to the Bay of Bengal. And so some good things about water, using it as a resource, but clearly contamination that's going to occur from this, if you're not careful about the rates at which you pump it, it's a problem. Exactly the same problems that you have in Florida. Florida is a very thin peninsula. You pump groundwater out of the limestone there. It pulls it in both from the Atlantic and the Gulf side. And if you pump too fast, then you end up messing up the resource that you would hope that you don't mess up. So another method. So I'll come back to this. You've seen a little picture a bit like this that I drew so expertly. The number one focus of this class is on contamination by non-aqueous fluids, because it's by far the most routine kind of contamination and most insidious kind of contamination, and possibly the most difficult to deal with, and one that just by happenstance deals with all the kinds of the most complex physics that you'd ever need, and everything is much simpler than this. So that's our reason for choosing it. For all of those reasons are legitimate reasons. But the basic idea is that if you spill a fluid which is denser than water into the subsurface, it will make a beeline through the aquifers. It will sit in a lens at the bottom in a puddle. It will leave a smear as it goes down, both through the vadose zone and through the saturated zone. And we need to know something about exactly what it will look like. We know that when you pour this stuff into bead packs in an aquarium in the lab, which is this, so take an aquarium, take the fish out, fill it with sand, put some water in it, fill some of this stuff into it, you end up with these very sketchy little streaks, these ganglia. Ganglion, I guess, is singular, ganglia are plural, in that it doesn't completely fill the space. And so the saturation that we talk about in this smeared zone isn't kind of a uniform saturation, but it occurs basically in individual streaks, some of which have relatively none of the smeared material, and some of them are quite effective pathways. We want to understand the mechanics by which that occurs. So most of the class we'll be trying to understand the mechanism by which it goes through the subsurface, sometimes in a vertical chimney, and then spreads out once it gets into the below the water table. In this. So we want to understand the processes by which that happens, both at kind of macroscopic scale, which is shown here, and also at microscopic scale. If you zoom in on portions of this and look at exactly what a portion of this might look like if you blow it up, then you find out that what's happened is that the water is present around the particles as a monolayer because it has an affinity to quartz, water wet, and that any contaminants that get in there will rest in some little pockets which look like this. And so understanding the mechanisms by which this happens is the key to understanding what's going on. And it's actually not very different from looking at the venometer. If you remember the venometer from 303, it's this little capillary tube that you can use to determine the alcohol content of wines, venometer. And it works by interfacial tension and how much force is applied between the glass of that tube, read quartz, quartz is just glass, and the liquid that's in it. So it's exactly the same behavior. So those are the kinds of things we'll talk about. So I do have a very quick, no, I didn't want to do that. A very few more things to say. So here, let me do this. Let me just go through this quickly. So a few points to make. So we'll talk in this class about contaminant hydrology. I work almost none of my time in contaminant hydrology. What I work in, which maybe you should never admit that, right, when you're talking about things, but I know lots about it. I certainly know more than you guys do, so that's all that's important. I work in energy fluids, the same as KJ does, and so my perspective on this is slightly different, but it's actually exactly the same physics that's involved. It's not being driven by gravity, it's being driven by fluid pressures, and the important questions that I'm interested in are slightly different from the ones we've talked about here, but let's just introduce them so you actually get some context outside this class as well in terms of what we'll talk about. These are a couple of quotes. Smalley is the Nobel laureate for buckyballs, the carbon-64 geodesic dome structure, who died young, a decade ago. And John Holdren was the president's science advisor in the White House, Obama's science advisor. I didn't realize till the other day that he was in the first class of MacArthur Fellows, Genius Grants. So you know those used to be, still is, I think, $500,000 to very bright people to go away and do whatever they want. First one was in 1981. I was surprised also that in the first one was also Lewis Gates, who's the guy who does this follow your ancestral tree stuff on PBS. Doesn't matter. But the point that these guys are both making is that energy and its responsible use, as in climate issues and Paris summit, is perhaps the most perplexing, one of the most perplexing problems of our time, in how to have low carbon energy sources without killing people's economies, and also being able to supply the roughly 10 or 15 terawatts of power that gets consumed on this planet worldwide, without creating large carbon issues. So you can read those quotes for yourself. And so there are a number of big picture views to how this might deal out, which is really happening as a result of market forces in some respects. And I think also as a result of Paris as well. It's kind of prompted it, the recent agreements in Paris to keep temperature changes below 2 degrees or 1.5 degrees is by limiting carbon into the atmosphere by certain amounts. And the ways you can do that are by a variety of ways. You can choose energy sources that are intrinsically either very low carbon or no carbon. And there are a number of those. My favorites are geothermal energy, where you use hot fluids in the subsurface instead of coal to heat up water. Nuclear waste disposal. Nuclear power is low carbon, not very popular. Still people worried by it, and has lots of problems related to disposal of wastes. contaminant hydrology problem. But the key issue in nuclear power is, one, how to build so many nuclear power plants quickly, and secondly is what to do with the waste. Thirdly, could be what happens if terrorists steal stuff in the reactors as well, kind of non-proliferation. And maybe the third, there are more than three, they're switching to renewables wholesale, of course, but the problem with renewables are that the capacity of renewables just isn't there compared to nuclear power, baseload power, geothermal energy, baseload power, if you can crack it, and the one which has happened actually driven by economics, which is gas. So right now, coal is out. Coal is high carbon per BTU. Gas is maybe half the carbon per BTU, and it's cheaper. It's dirt cheap through Marcellus, and it's displacing coal not only because of the Clean Power Plan from Obama and the EPA, which says that all states have to reduce their emissions, but just by the cost. Gas is so cheap, it's gone down from maybe $8 to $10 per 1,000 cubic feet to maybe of the order of high twos to $3, a third of the price. And so it's cheaper to burn it than coal because it's so abundant. And it's also cleaner than coal because it's CH4. It has many fewer carbons to every hydrogen than does coal. And so it's happening naturally. And so the mechanisms by which this transformation is occurring has strong connections to fluids for the reasons we'll talk about. Geothermal, for obvious reasons. Drill a hole down 5 kilometers, make a reservoir everywhere, including underneath us, our feet right now. Drill a second hole down to intersect that reservoir and circulate water in a big geological heat exchanger. The actual size of the resource, I guess I can't write on this because it's not the right one. Why can't I write on this? That's why I can't write on it. Yeah. So the size of the resource is just amazing. It's huge. You can do the calculations with, this is exajoules, 10 to the 18 joules. It's huge. And so if this can ever be cracked as a method, no pun intended, as a method to do this, then got it made in the shade. Don't have to worry about coal. Don't have to worry about gas and oil. Actually, you do, because you need them for transportation fuels, right? Tough to fly a plane on electricity, on batteries so far. But you need these really high energy density fuels rather than this. But of course, if you get electricity, you could make those fuels. You could reform them. So geothermal energy, push water in through a cold hole, flow it across a reservoir, tap it out on a warm hole. Once it's picked up the heat, take it to the surface, run it through turbines, generate electricity, make it cold, push it back down again, have a closed circuit solution. Lots of interesting problems, but basically it's an energy fluids problem, no different from the things that we'll talk about in this class. Pushing fluids through porous and fractured media, which they might react with, and from which they can take temperature out. We won't take a temperature out. Nuclear power. There are a variety of problems with nuclear power, not least of which are reactors exploding, like Fukushima, like 3 Mile Island, 90 miles from here, right, from 1979, and Chernobyl from 1986 in Ukraine. But apart from the issues of making the reactors so they're fail-safe, you can do that now. One of the issues is what you do with the waste. It used to be that the solution was, or still is worldwide, the solution is to mine out tunnels maybe 300 or 300 meters or 1,000 meters below the surface into arrays of tunnels that you just drive railroad trains that have big canisters, the same size as those, the Procore black gas tankers that you see on the railways these days that kind of have a habit of exploding in cities these days. Canisters the size of that. You take them underground, you immobilize them, you backfill around them, you completely backfill all the tunnels, and you leave it for 1 million years, which is the time that EPA has defined that you have to design this thing to contain the wastes. Every developed nation in the West has a plan to do this. It was the plan for the US as well, for Yucca Mountain, until After the election of the president in 2008, Yucca Mountain as a repository was stopped, primarily because Nevada and its very influential senator did not want the stuff to reside in Nevada. And that senator might have been an important senator in healthcare votes. And so it was shelved with a blue ribbon plan. Now it turns out that the preferred thought for a mechanism to store it is, instead of doing it in repositories which are mined out and then you store the material underground in these parallel tunnels, maybe they're the diameter of this room, maybe they run for 2 kilometers, a mile, and you fill it up with these railroad cars and backfill, and then have another one of these, another 50 meters to the left of you, and another 50 meters to the left of you, so it looks like a grid like this. The preferred method that's being investigated now is to drill very deep boreholes, maybe 5 kilometers deep, that are probably half a meter in diameter, something like that. You have these circular canisters that contain the waste, and you drop them into the subsurface. Drop them to the bottom of the hole, you put a number of them there, and then you seal it, and then you just forget about it. So that's the one. The US is the only country investigating that right now, but that seems like the preferred option. And again, the only mechanism by which that could escape, either from this geometry or from this deep borehole geometry, the canisters will break over time. You can't guarantee that they won't. If they do break, you want to have the idea that you have these multiple barriers. So you have the waste package, which is vitrified, so it doesn't leach out very easily because it's a glass. It's inside a copper container, which is quite thick, maybe an inch thick, which is also resistant, ductile and resistant to deformation, and also contains the material inside it. That canister is inside bentonite clay, which is very low permeability. It lets water through only very slowly, and also self-heals. So if you deform it and crack it, it will actually heal itself. And then outside that, you make sure that the stuff you put it into, the granite at 5 kilometers, is a really, really low permeability, so that if it gets through those sequential barriers, then it can't go to hurt anybody once it's there. So the basic idea is that. Oops. If you do burn coal, so the way of getting nuclear waste to the biosphere is by water transport. If you do want to burn coal, one way to do it and still burn coal is to take the CO2 that comes out the stack, pump it underground, make sure it stays in place. Lots of schemes to do that. There are some that are actively doing that. Maybe 1 million tons per year is their capacity. The need for the worldwide consumption is something like 40 gigatons. So we're doing 1 million tons a year in 3 or 4 places around the globe. We need to do something like 40 billion tons per year. So the scale up is 3 orders of magnitude to be able to do that. But feasibly it could happen. The mechanics of doing that are putting it into old petroleum reservoirs or saline aquifers or coal beds and hoping that it stays there. And that would allow you to still burn coal, of which many countries have big reserves, or burn natural gas, which has lower carbon out of the stack, but you still might like to get rid of the CO2 that does come out to be able to keep on using fossil fuels. And natural gas, of course, is the wonder fuel of the last decade through the bulk of your lifetime. It's been the last 10 years, which has displaced coal as a matter of fact, but has its own problems. People worry about the connection of hydraulic fractures with aquifers, even though they're quite far separated. Maybe in Pennsylvania, these holes are 3 kilometers deep. The potable water is maybe 500 meters deep. So 3 kilometers, 3,000 meters versus 500 meters. And so there's a very big distance between that, but is an issue. And gas has been found in groundwater, primarily through where the wells come up through the aquifers themselves, not from the hydraulic fracturing features in these horizontal wells, where, of course, horizontal wells and massive hydraulic fracturing was the technology developed by Mitchell, which made all of a sudden the gas locked up in these shales that had been there for millions of years because it was so impermeable, all of a sudden able to be recovered by hydraulic fracturing. And so hydraulic fracturing is the method by which it's done, but people are worried by the fact that the agents which are used to wash proppants into the fractures, you pump up the well bore, it drives a hydraulic fracture into that fracture, so when you back off the pressure, it doesn't just deflate and close. You wash sand into it as proppant, and you wash that sand typically with water and sand, but also you put in some other things. The other things are things like bactericides to stop bio growth in the subsurface. There are things like friction reducers that make it much more slippery, so that the pressure that you apply on the well pad at the top of the well actually gets its way down to the bottom. You know from your fluid mechanics that if you have viscous resistance along the pipe, then the fluid pressure you apply at the top is not the fluid pressure you see at the bottom, because it gets eaten up by the viscous resistance all the way along the pipe. And so if you reduce that viscous resistance, all of a sudden the pressure you apply at the top is the pressure you apply at the bottom, and therefore is the pressure that you can use to split the rock open at the bottom. And so these things were not disclosed, are now required to be disclosed as to what the actual makeup of these components are. And there is some worry that some of these things ultimately might get itself into the groundwater. Even though I think so far there have been no incidences recorded of where it has got into the groundwater from these depths, but it has been recorded where it's got into groundwater from the wells as it comes up through the aquifers. So, and some people would argue that there's just not enough data out there to be able to say one way or the other, which may actually be a decent argument. Is actually a decent argument. And I'm going to leave it there. So those are my favorite energy fluids. And so although I work sparingly, I would say, on contaminant hydrology, as I say, I know more than you, and that's all that counts in this deal, I think. So that'll be our focus. And so to reiterate, we work on multi-phase fluids, L-NAPL, lighter than water, non-aqueous phase liquids, D-NAPL, denser than water, non-aqueous phase liquids, because they are contemporary contaminants. They're the most difficult problems to deal with, and they're the most difficult physical problems to solve. If you understand the physics of those systems, you understand everything else. And so that's where we'll take it. Next time we'll talk about multi-phase flow, and so we'll start dealing with the meat of the class. We will hand out a sign-up sheet. Hope you will all be here next Thursday. If not, that's fine. If you're not, then you do have to complete the recording, and we'll do it on some kind of time frame that we'll let you know. Your friends can let you know if you're not here. Okay? Enjoy the snow. Thanks so much. Any questions? All right. Great, thanks.